Hello viewers, in this video we are starting problem number 36 of GR0177 problem. The problem is, consider a quasi-static adiabatic expansion of an ideal gas from initial state I to final state F. Which of the following statement is not true? We have a gas which expand adiabatically from state first I to final state F. In which of the following statement of below is not true? The very first statement is no heat flows, N2 are out of the gas. This is the definition of adiabatic process and quasi-static process, that there is a very small change and the process is adiabatic, means no heat is enter or leave the system. Option 1 is true. We have to find the option that is not true. The second option, the entropy of the state I first state equal to the entropy of the second state. For this, entropy by definition given by dQ by d by T. This is the change in heat dQ, but in this process there is no change in heat, so there is no change in entropy. So final entropy equal to entropy of the second state. So this is also true. The third one is, the change of internal energy of the gas is minus integral P dV. For this, from first law of thermodynamics, dQ, this is equal to du plus integral P dV. In this case, dQ is 0 because the process is adiabatic, so this is equal to 0 du plus integral P dV. This implies that du, this is equal to minus integral of P dV. So this option is also right option. This is also true. Option D, the mechanical work done by the gas is rho integral P dV. So this is also the right option. The work done by the gas is always equal to P dV. The last option is, the temperature of the gas remain constant. For this we have that PV gamma is equal to constant, but here PV, this is equal to N or T. If we put this value in this equation, then TV power gamma minus 1, this is equal to constant. This implies that T1 Ti of state initial state and V of initial state gamma minus 1, this is equal to T of final state and V of final state power gamma minus 1. This equation implies that the temperature of final state is not equal to temperature of this final state, mean temperature of this gas is not constant. So the option E is our right option. In this option, the temperature of the system does not remain constant, so this option is not true out of the 5. Next problem is 37. A constant amount of ideal gas undergoes a cyclic process A, B, C, A in a PV diagram in a figure. The path BC is isothermal. The work done by the gas during one complete cycle, beginning and ending at A, is most nearly. The diagram is given here. A cyclic process starts from A to B, from B to C, and C to A. The total work done we have to find in this diagram. In this diagram, if we see, there are 3 paths, so the total work done will be equal to the sum of work done by these 3 paths. So this will be equal to W from A to B plus work done from B to C plus work done from C to A. If we see in this figure, first of all, we have given volume at A but not at B. So pressure is also given at these 2 points. According to Gauss law, PA this is equal to PB implies that volume at B this is equal to PA divided by PB. Here we have to find volume here. So PA is 500 at point A. Their volume is 2 but pressure is 500 divided by 2 divided by pressure is 200. So 5 meter cube is volume at B. So VB this is equal to 5 meter cube. Here 5. Now we have 3 paths to find work done. First of all, if we see from C to A, there is no work because there is no expansion in volume, so this term will goes to 0. Now the work done from A to B, if we see work done from A to B, this is equal to P of VB minus VA. Change in volume when it goes from A to B, and pressure at that point is 200. So this is 200 and 2, this is 5 minus 2 equal to 600 joule. So this is the work done at this point, kilojoule, because pressure is in kilopascal. Now the work done from B to C, this is equal to work done from B to C, because this is isothermal process from BC curve, so this is equal to PdV. Here we know that PV this is equal to nRT, so P this is equal to nRT by V. Put here integral nRT over V dV, this is equal to nRT integral ln of VA over VB. This is from A to B, from B to VB to VA. So this is our work done when we move from B to C. Putting values here, nRT this is equal to PV, nRT this is equal to PV at this place or at this place. So this is W work done from B to C, this is equal to PV integral ln of VA over VB. PV P at or V at this place, so this is 200 multiplied by 5 multiplied by ln of 2 over 5. This is 1000 multiplied by ln of 2 by 5 are approximately equal to minus 0.99, minus 0.9 approximately. So if you will multiply it, this is approximately equal to minus 900. So the total work done according to equation 1 is equal to work done from A to B plus work done from B to C, work done from C to A. This is 0, so this is 600 minus 900, so this is equal to minus 300 kilojoule. So the work done in this whole process, in cyclic process, is approximately equal to minus 300 kilojoule. So option D is right option in this problem. Here you can also take PV. I have taken the value at point B. You can also we can take the value at C. So this will be 500 multiplied by 2, so this is again equal to 1000. We are taking value of pressure and volume at one place, this here or here in this process, in this isothermal curve. Next problem is 38. An EC circuit consists of elements in figure with a resistance 10,000 ohm and inductance L 25 millihenry, and C in adjustable capacitance. Here this is a diagram for this circuit. This is RLC circuit. There are three components in this circuit: resistance, inductance and capacitance. All are in series. So the AC voltage generator supplies a signal. This is AC voltage generator connected with this circuit, which have 40 volts its amplitude, and angular frequency is 1000 radian per second. For what value of C is the amplitude of the current maximized? This is series RLC circuit, which is used for resonance purpose. Here the capacitance is adjustable, so we have to find the value of capacitance C when it current amplitude is maximized. So for this we will use resonance principle. The inductive reactance of inductor is equal to omega L, and capacitive reactance of this circuit capacitor in this circuit is equal to 1 over omega C, where omega is the angular frequency. For resistor, reactance is simply equal to R. So this is a steady component. There is no change in amplitude because of this. So these two are responsible, these two reactants are responsible for the change in amplitude of currents. So for resonance purpose, for resonance, the condition is inductive reactance must equal to capacitive reactance. We will compare these two. Omega L, this is equal to 1 over omega C. This implies that C is equal to 1 divided by omega square L. We have these two values. 1 divided by omega is 1000, so we can write 10 power 3 whole square multiplied by, or inductance is 25 millihenry, we can write 25 multiplied by 10 power minus 3. If we solve this, then we get 1 divided by 25,000. This is equal to 40 microfarad. This will be equal to 40 multiplied by 10 power 6 farad. We can write 40 microfarad. If we adjust the value of this capacitance is equal to 40 microfarad, then the current amplitude will be maximized. So 40 microfarad, D is right option. Next problem is 39. Which two of the following circuits are high pass filters? There are 4 circuits given. Which two of these 4 are high pass filter we have to find? For this we will use 3 formulas. The very first is V out, this is equal to x2 divided by x1 plus x2 and 2 Vn. This is voltage divider formula. The output voltage we will get out of the input voltage by this formula. X2 is this one. In each case, this component is x2 and this component is x1. And second, inductive reactance, this is equal to omega L, and capacitive reactance, this is equal to 1 over omega C. We will use these 3 formulas to find out that which one are high pass filter. High pass filter are those filter which pass high frequency and stop low frequency voltage. High pass filter will always pass high frequency voltage and will stop low frequency voltage. Now from the very first, if we see that there is inductor in series, if we increase omega, this is angular frequency, XL will also increase. If it increase, then X1 will increases. This is X1 component reactance of inductor, and this is x2. If it increase, if x1 increases with increase in frequency, a time will reach when x1 will become infinite, so x2 and to Vn, then Vout will become 0. This term will undefined, so x2 divided by undefined is equal to 0. So with increasing angular frequency, the reactance of inductor increases. So increasing this reactance, it will stop the high voltages, high frequency voltage. So it will stop high frequency and will pass low frequency. So this is low pass. This is low pass filter. And the second option, if we see that this is resistance which is independent of frequency, and this is inductor which is dependent of frequency. If we have low frequency, then it have low value, so voltage will come out of this way. So there will be no voltage at these 2 points. So this will be short for low frequency, so this will stop low frequency voltage. But if we increase this frequency, angular frequency, it will also increase XL. If XL increases, then this is the value of x2. So in this case, V out, this is equal to x2 divided by x1 plus x2. If x2 increases, a time will reach when x1 plus x2, this will approximately equal to x2. If x2 is very high than x1, then x1 plus x2, this is equal to x2. So x2 divided by x2, this will equal to 1. This term will become equal to 1. So V out, this will be Vn. At low frequency, it stop the voltage, but at high frequency, its output is equal to input at pass. So this is high pass. This is high pass. Now in third one, if we see, here is a capacitor. The inductive capacitive reactance, this is inversely proportional to angular frequency. If we increase angular frequency, this is increases, so this will stop the voltage. But at low frequency, this will stop, because at low frequency the capacitive reactance will be much higher. If it is very much higher, then x2 divided by x1 plus x2, there Vn is equal to V out. X1 is this. If it is much higher, then this will goes to infinity. So x1 plus x2 will be very greater than x2. So this term will goes to 0. So V output will be goes to 0 at low frequency. But at high frequency, this term will become very small. If this is much small, then x1 plus x2, this is approximately equal to x2. So this term will goes to 1. If this term goes to 1 when x2 is much higher and x1 is much smaller, or x2 is much higher, then V output is equal to Vn. So at low frequency, this term goes to 0. At high frequency, this term goes to 1. So at high frequency it will pass voltage, but at low frequency it will stop. So this is also high pass. And the fourth one, if we see, this is capacitance. So this is the reciprocal of this. If frequency is small, in this case x2 divided by x1 plus x2, this is x2. Now if frequency is very low, this is much higher. If this is much higher, then x1 plus x2 is approximately equal to x2. This term will goes to 1 at low frequency. So it means it will pass the voltage at low frequency. But at higher frequency, this term will become very small. So this term will goes to 0. If omega is very less. and f omega is very greater, so this goes to 1. Now in these four, these two, second and third, are high pass, so this option is right option D, in which second and third are high pass circuits. Next is problem 40. In circuit shown above, the switch S is closed at t is equal to 0. Which of the following best represent the voltage across the inductor as seen on an oscilloscope? Here this is a circuit diagram. This is switch S, this is inductor of 10 millihenry, and this is resistance of 2 ohm. 10 volt battery is attached to the circuit, to the series circuit. So we have to find the voltage time plot for this oscillation. This circuit is seen on oscilloscope. So first of all, the voltage across inductor is equal to minus L di by dt. Inductance multiplied by rate of change of current, this is the voltage across inductor in a circuit. If this was a purely resistive circuit, then epsilon, this is equal to IR. Two components in this circuit, inductor and a resistor. So we are using Kirchhoff voltage law for this. Then epsilon, this is equal to voltage, this is equal to EMF, this is equal to voltage drop across resistor plus voltage drop across the inductor. This is L di by dt. This is according to Kirchhoff. This is, if we use Kirchhoff voltage law, EMF, this is equal to across the circuit, this is equal to voltage drop across the component, sum of voltage drop across the components. If we solve this first order differential equation, we will get this solution for current. Now we have to find the plot that best represent this current on the screen of oscilloscope. Now we are dealing with this term. We can see that this is exponential function, so the plot must be exponential, but this is a decreasing exponential function. This is negative sign, so the plot must be decreasing exponential function. So these two options may be right. One of these two may be right. These two or three options are wrong, because these are increasing exponential and this is decaying exponential process equation. So D or E, one of them will be right option. Now second, we are dealing with, this is R over L. Let we thaw time L, time factor L, this is equal to L over R. Let tau L is the time factor for this equation. Time factor is a time in which half of the current decay or rise. The time required to rise or time required to fall, the half of the total current. So this is L over R. L is given 10 divided by R2, this is equal to 5 milliseconds. So we will find 5 milliseconds time factor in these graphs. So this is D. D is the right option. D is decaying exponentially and its time factor is 5 milliseconds. So D is right option. Here this is decaying exponential function, but the time factor is 200 milliseconds. So this is wrong. This D, option D, is right option. This is the last problem of this video. Please like, share and subscribe.